In this video tutorial, we're going to be talking about the Chow test for detecting a structural break in a time series. The Chow test basically allows us to detect if there has been a significant deviation in our time series, a significant move away from the trend. And the data set that we're going to be using for this example is heart rate per minute. So you can see that for the time variable we have intervals of 10 minutes. Then we have the number of beats of a person per minute, the heart rate per minute, as well as the steps taken by that person per minute. And we can see that the heart rate per minute is more or less constant, but as we go down, we can see a jump in heart rate just at time period 33, and that's also related to a jump in the number of steps taken per minute. So that seems a logical relationship. As physical exertion increases, so does the number of beats per minute. Now, the reason that we're going to be using this data set to conduct the Chow test is because it's an ideal data set to be able to screen for a structural change in the time series, because if we have a look at the heart rate per minute, I'm just going to make this plot a bit bigger here. With the exception of this part here, this big jump, this deviation away from the structural trend, we can see that we have more or less a stationary series. By stationary, we mean a constant mean and variance. So when a person is at rest, typically their heart rate is not going to deviate all that much, save for something unusual like an illness or something like that. So heart rate is going to remain more or less constant at the resting heart rate. But where the Chow test comes in is it's able to detect whether a structural change exists or not. So we might see a jump in a particular time series, and we want to verify, is that in fact a structural break? From this plot it's obvious that it is, but in other graphs it might not be so obvious. So the Chow test is the formal test for detecting that. So when we run our Chow test, we are running 3 different regressions. So we have here Reg P, which is our pooled regression, Reg A, which is our regression which is done on the observations before the structural change, Reg B is done on the observations after the structural change, and the pooled regression takes observations both before the jump in heart rate and after the jump in heart rate. So it's taking into account the observations before and after the structural change. So when we run these 3 regressions, we can see that for the pooled regression anyway, we have a positive and significant correlation between the steps taken per minute and the heart rate per minute, which is logical. We'd expect that the more a person exerts themselves, the more you're going to see heart rate rising. And we're also calculating, for the purpose of the Chow statistic, the degrees of freedom in our model. So for example, for regression B, when we calculate the degrees of freedom, we're using reg B $df, and that's giving us the number of degrees of freedom in our regression. We're also calculating the residual sum of squares for each regression. So RSSP is the residual sum of squares for our pooled regression, residual sum for A, and residual sum for B as well. So the reason that we want to calculate these is because we are going to be factoring these in to our Chow statistic calculation. So we can see here that when it comes to calculating the Chow statistic, we have the residual sum of squares for the pooled regression minus the sum of the residual sum of squares for A and B. We're dividing that by k being the number of variables in our regression model, which includes the intercept. In this case, it's 2. We're dividing that by the sum of the residual sum squares for a and b, and in turn dividing that by the sum of the degrees of freedom for a, the degrees of freedom for b, minus 2 multiplied by k. So when we conduct that calculation, we can see that we get a Chow statistic of 64.46 in this case. And what we want to do is we want to compare that to our F critical value. So when we use R, we calculate our F critical value at the 5% significance level or the 95% confidence level using the QF command, and we're factoring in the number of degrees of freedom for A and the number of degrees of freedom for B. And we see here that when we calculate our F critical value, it's way lower than the Chow statistic that we calculated, so 3.178. So because our Chow statistic is a lot larger than the F critical value, it means that we reject the null hypothesis of no structural break. So on the basis of the data that we have here, we can conclude with 95% confidence that a structural break exists in our time series. And when we look down here, when we've done a second Chow test, we've taken the reg p, which is the pooled regression from 1 to 30, and these observations are before we have the jump in the heart rate. So our pooled regression is observations 1 to 30. Our regression A is 1 to 15. Our regression B is 16 to 30. So we expect that when we run this Chow test, we expect that we won't be able to reject the null hypothesis of no structural change because we can't detect a structural change for the first 30 observations. So if we go down here, because the method is the same as above, again, we're calculating the Chow statistic 0.19 and the F critical value of 2.57. So in this case, we can see that the Chow statistic is less than the F critical value. So this means that this time, as expected, we do not reject the null hypothesis of no structural change. And based on the 95% confidence level, we conclude that no structural change exists in this model. So that's how the Chow test can be used in order to detect a structural change within time series models. Admittedly, this is an overly simplistic example because we can see that very clearly there is a structural change in the time series, but there are times where it won't be so evident from the graph that a structural change exists, and we're going to want to formally test for that, and the Chow test is a good way to do that. So that concludes this tutorial. Hope you enjoyed it, and if you have any questions regarding the material I've covered, please feel free to leave a comment or even email me personally or check out this tutorial on my website. Many thanks and see you next time.